In this lesson, we are going to spend some time talking about a very important topic in chemistry called nomenclature. Nomenclature is a word that simply means the rules for writing formulas and naming compounds. Now, in this objective, we are going to talk about 5 different classes. 4 of them are ionic compounds. Okay, and the 4 subcategories are simple ionic, transition metals, polyatomic ions, and acids. And then we will talk about covalent compounds. Now, I highly suggest that as you learn about each class of compounds, the nomenclature associated with that you then pause this video or stop this video and then go do that particular section in your nomenclature packet. At the end, we will talk about the way to determine what type of compound you are looking at if they're all mixed up together. In your quiz, you'll have sections that will be labeled with each. Okay, but once you move forward a little bit, you will no longer be simply told this is a simple ionic compound. You'll have to recognize it and name it as what's appropriate. Okay, so to do this, you're definitely going to need your periodic table. Now remember, in one of our previous lessons, we talked about the oxidation numbers for the different families on the periodic table. Remember, this family is the alkali metal family with an oxidation number of +1. Okay, and hydrogen is positive or -1. Because remember, hydrogen is a very unusual compound. Hydrogen has the ability to behave as though it were a metal and give away its valence electron and have an oxidation number of +1. It also can behave like a normal nonmetal, and it could take an extra valence electron and have a charge of -1. Okay, when it becomes metallic, when it behaves metallically, that's a particular class of compounds that we're going to talk about in a little bit. Okay, let's move on. Here's the alkali earth metals. Okay, and previously we said that the oxidation number is a variable. What I want you to do right now on your periodic table is write that the oxidation number is equivalent to a Roman numeral. And in a little bit, we're going to talk about transition metal compounds, and we'll elaborate a little further. Okay, let's keep going. This is the boron family, okay, with oxidation number of +3. The carbon family, remember we said those that are metallic, that's germanium, tin, and lead, would be +4, and those that were non-metallic, that would be carbon and silicon, are -4. Then moving on to nitrogen, okay, the majority of them are -3. Antimony and bismuth. Antimony actually behaves fairly non-metallically. Bismuth is a metal, and it would have a +3 charge. Oxygen family, -2, and the fluorine family, -1. Okay, the noble gases have an oxidation state of 0, but we're going to ignore the noble gases in this objective because we're going to talk about compounds, which means we're bonding together elements, and the noble gases do not bond. Okay, now that we have that, okay, we are now going to move on and talk about the simple ionic compounds. Simple ionic compounds are metals from the alkali, alkali earth, or aluminum families. Excuse me, boron family. okay, plus a nonmetal. Okay, it's very important in order to do well on this that you be able to look at element and know if it's a metal or a nonmetal. Okay, on your periodic table, you should have, if you haven't drawn it in already, you need to draw it in. Okay, the stair-step line. It's a little hard to draw a straight line here. Okay, you should have this drawn in. If you don't, you need to do it now because you're going to need to. Okay, if you're using the multicolored periodic tables from the Navy, I highly suggest that instead you use the white ones that I hand you out in class because there's a lot more easy to write on and mark up than the one from the military. Okay, so simple ionic compounds have a metal and a nonmetal. And first of all, we're going to talk about how to name these compounds. Naming a compound, you simply name the metal, okay, and you're going to change the nonmetal to an IDE ending. Okay, so what does that look like? This is a simple ionic compound. Okay, sodium comes from the alkali metal family, and chlorine is a nonmetal. So the name of this compound is sodium. Okay. Okay, the chlorine ending gets changed to chloride instead. So this is called sodium chloride. Okay, this compound right here, this is the metal beryllium. This comes from the alkali earth metal family. This is the nonmetal fluorine, and you're going to change the fluorine to fluoride. Okay, all nonmetal ions have their names changed to IDE. The ending of their name is IDE. Now, why do you see a 2 here? Well, that's important, and let's talk about the formulas. Okay, when we write formulas, the positive and negative charge in the compound must cancel. So when you look at the oxidation numbers, occasionally you'll discover that they're not going to come together in a ratio of 1 to 1. So for example, let us look at the compound called aluminum bromide. Now, when you see the names, you write down the symbols and be very careful that you write the correct symbols, because you know that right now that there are some elements whose symbols are similar and they get mixed up. For example, sodium is not S, sodium is Na. Sulfur is S. You need to very carefully watch that. Okay, bromide, okay, must be the ion of the element bromine. Now, after you write the symbols down, you go to your periodic table and you ask yourself, what's the oxidation number of each one? Okay, aluminum is oxidation number 3. Bromine, right here, is oxidation number -1. Okay, so I'm going to write that really small up here, +3 and -1. Now, they have to have the same amount of positive or negative charge. So if it's 1 aluminum ion and 1 bromine ion, that would be +3 and -1. That does not cancel to 0. So what I need is I need to increase the total negative charge from the bromine ions to -3. That means I need 3 bromine ions. So the formula, when you write the formula, the oxidation numbers disappear. That's AlBr3. So 1 aluminum ion will pair up with 3 bromine ions when the compound is formed. Okay, now we do not write a subscript of 1. Okay, so do not do that. Now, the shortcut method for doing these is called the crisscross method. I'll show you that a little bit here. Okay, let's look at another compound. It's potassium oxide. Okay, you can probably guess that oxide is the name of the oxygen ion. Okay, so let's write our symbols. Potassium, if you look at your periodic table, is K. And of course the oxide ion would be O. Potassium is a member of the alkali metal family, so it's positive 1. Oxygen is a member of the oxygen family, it's negative 2. Okay, obviously those do not cancel out. So I need to increase the number of potassium ions so that it's also positive 2, meaning I need 2 potassium ions. So this formula becomes K2O. Now, this shows you the crisscross method. The crisscross method simply means that you take the oxidation numbers, okay, and you switch them. But you don't include positive or negative signs when you switch them and make them. These are called subscripts. These numbers that are written down below in the formula are called a subscript. They always belong to the number. They're always just to the right of the element that they belong to. So this is K2O. This is the 2 has nothing to do with the oxygen. Be real careful with that. Okay, so the 1 and the 2 get switched. Now it's 2 and 1. Remember, the 1s are invisible in the formula, so just simply we don't write them. It's a little lazy. Okay, let's do a couple of other examples. Let's do gallium. Sulfide. Okay, so gallium is Ga. Sulfide is the sulfur ion. Gas. Look at your periodic table. Gallium is a member of the aluminum boron family, so it's 3. Sulfur is a member of the oxygen family, so it's negative 2. Now those do not cancel out. So I'm going to switch them. So the 2 is going to come down here, see, 2 here, and the 3 goes across here. It's called the crisscross method because we kind of cross them, but we switch them. That's where we're going. So the formula for gallium sulfide would be Ga2S3. Make sure when you write your final formulas that the oxidation numbers have been removed. Okay, you do not, after a while, if you get very comfortable and you're doing these correctly, you do not need to write out kind of the, this is kind of like showing your work a little bit for math. Okay, that's not required as long as you have correct formulas. All right, let's do one more. Let's do lithium iodide. Okay, if you find lithium, lithium is a member of the alkali metal family, it's Li. Iodine is a member of the halogen family. Its symbol is I. Okay, so this one has a positive 1. This one has a negative 1. These two numbers cancel out, meaning just the 2 symbols are all you need. Okay? If you find the oxidation numbers cancel out, just write the 2 symbols next to each other and you're done. Okay, so before you go on, a couple of notes for some of the non-metal ions. Okay, remember oxygen is called oxide. Sulfur is called sulfide. Okay, nitrogen is called nitride. Okay, so you're going to practice these a little bit, so I highly suggest you pause or stop the video go to the worksheet that says simple ionic compounds. You'll have some practice naming and some practice writing formulas. Our next group of compounds are called the transition metal compounds. Okay, these have metals from the transition metal family. Okay. Plus some of the nonmetal ions. Now, the reason that these are so unusual is that they have varying oxidation numbers. So some of the family members have 2 or more oxidation numbers possible. For example, iron can be positive 2, or iron can sometimes be positive 3. The reason this is possible is, for the transition metals, it's kind of unusual because they have those electrons in those d orbitals, and those can behave occasionally as though they were valence electrons. So how are you supposed to tell if the iron in a compound has an oxidation number of positive 2 or if it has an oxidation number of positive 3? Okay, what we do is we include a Roman numeral to show the oxidation number. Since they don't have the same oxidation number every time, we have to include something extra. So what that means is Fe plus 2 is called iron 2, and Fe plus 3 is called iron 3. You need to make sure that you know the Roman numerals 1 through 7. Okay, 1, 2, 3, 4, 5, 6, 7. You won't have to work with anything higher than that. Okay, don't forget to not mix up 4 and 6. 4 is IV, 6 is VI. That's very, very important that you not remember that. All right, so let's look at the naming. And then we'll look at formula writing. Okay, when you name these, you have to figure out the oxidation number on the metal. And the way you do it is by looking at the nonmetal. Okay, and the oxidation number becomes the Roman numeral. Okay, so for example, Cu is the transition metal copper, and this is O, and the oxygen ion is called oxide. Now, anytime you're trying to name an oxidation metal compound, the first thing you do is look up the nonmetal. Oxygen is a -2. Now, if you look very carefully at the compound has 1 copper ion and 1 oxygen ion. Okay, that means if there's 1 of each, it means they have the same oxidation number. They're just one's positive, one's negative. So that means that the copper is positive 2. So that's going to become a Roman numeral. Remember, the Roman numeral is always the oxidation number. What about this formula? This is vanadium something oxide. Okay, vanadium is another oxidation transition metal, and this is oxide again. You do the same thing. Okay? If you look up O, it's negative 2. Now if you have numbers here, that means that they were crisscrossed. So to find out the Roman numeral, you have to uncrisscross them. Okay, the 2 obviously came down here. So where did the 3 come from? The 3 had to come off of the vanadium. So that means it's vanadium 3. Okay, let's do a couple more examples, and then we'll do some formula writing. Okay, Zn is a transition metal zinc, and I would be the iodide ion. Okay, you go to the periodic table, always look up the nonmetal. It's negative 1. Okay, well, then where did the 2 come from? Okay, remember, you're uncrisscrossing. There's nothing here because that's the 1. So this 2 had to come from the zinc. That means it's zinc 2 iodide. Okay, this is iron. This is N, meaning that's the nitride ion. Nitride is the name of the nitrogen ion. Okay, you go to the periodic table and you look up N. N is negative 3. Okay, there's no numbers. That means that the oxidation numbers had to be the same. So the iron is positive 3. So this is iron 3 nitride. Okay, you're not going to see a whole lot of fancy things. It's going to be 1, 2 is the most common oxidation number over all the transition metals. But you'll see 2, 3, 4, 5, occasionally 6 and 7, but those are pretty rare. Okay, formulas. The thing you have to remember is the Roman numeral is the oxidation number for the metal. Okay, so if it says scandium, Roman numeral 1, telluride, you go to the periodic table and you say, okay, scandium is Sc, telluride must be the tellurium ion, that's Te. Okay, this one has an oxidation number of negative 2. This means that scandium is positive 1. This is scandium 1. Remember, the Roman numeral always belongs to the metal. So these are not the same, so you're going to have to crisscross them, meaning the 2 comes down here, the 1 disappears. Your formula is Sc2Te. Iron 3 sulfide. Iron is Fe. Sulfide is the name of the sulfur ion. The Roman numeral 3 means it's Fe positive 3. You look up sulfur, it's negative 2. You're going to need to crisscross them, so the 2 comes down here, and the 3 comes over here. So your final formula is Fe2S3. Okay, do not forget, your final formula cannot have any oxidation numbers in it. You need to drop those off. Okay, I suggest you pause or stop the video and go to your nomenclature packet and do the page that says transition metal compounds. Our next group of compounds is going to require you to turn over the white periodic table I gave you and look at the list of polyatomic ions on the back. Now, polyatomic ions are a group of nonmetals which are covalently bonded together but still need to accept additional electrons to become stable. So they bond together covalently, but they can't quite get enough valence electrons for everybody to have the exact same electron configuration as a noble gas. So they need them from somewhere else, meaning they become negative ions. But they're a group rather than a single atom. So that's what the word polyatomic means. It means many atoms. There is one exception if you look very carefully. The exception is ammonium. It's positive. Now that's a group that ends up with an extra valence electron and has to give it away. Okay, on the back of your periodic table is the formula of the group, which can never change, and the oxidation number is given there. For example, if you look at your back of your periodic table, sulfate says SO4 -2. So this is the group sulfate. It's a sulfur and 4 oxygens. They have to take 2 extra electrons that have a -2 charge. Now, many of the polyatomic ions have similar names because they have similar formulas. For example, sulfite is similar to sulfate, except it has 1 less oxygen. That's SO3 with a -2 charge. Okay, so you will have to get comfortable with these. This is phosphate, PO4, so phosphorus and 4 oxygen. They need to take 3 extra valence electrons to become -3. You'll have to recognize these because their endings are slightly different. They end in ATE or ITE. Okay, there are a few exceptions, and that would be cyanide, hydroxide, and ammonium. Those are some of the exceptions. Okay, naming these are very easy. You simply name the positive ion, okay, and then name the negative ion. Okay, 9 times out of 10, the polyatomic ion is the negative ion. So for example, KMNO4. Okay. K is potassium. This whole group right here is on the back of your periodic table. This is called permanganate. Okay, this is a super tricky one. There's a funny one on the back of your table. Oh, that's another one I should add up here. That ends with IDE. It's called peroxide. Okay. You can tell that it's peroxide because if you look at it and you say if it was just sodium oxide, there would be no 2 here because that would be +1 and -2. This is O2 -2. So this is a little odd one. Sodium peroxide. Okay, one more example. Okay, this piece here is the polyatomic ion. You just have to get comfortable with these. Spend some time. Okay, that one's called oxalate, C2O4, magnesium oxalate. Okay, writing formulas. It's pretty straightforward. You're just gonna do crisscross the oxidation numbers. But you have to put the formulas of the polyatomic ions you're going to enclose them in parentheses. Unless you crisscross with one, or they're going to cancel. Show you what that looks like. Okay, so for example, okay, this is ammonium, which as you'll learn is NH4. Okay, and it's plus, which is the same as +1. And sulfide is the name of the sulfur ion, which is -2. Now, you need to crisscross these because they don't cancel out. But you cannot simply write a 2 here because it looks like NH42, and that's not right. So we're going to put the NH4 in parentheses, and then we'll add a 2. So the formula for ammonium sulfide is NH4 Roman parentheses 2S. Calcium nitrate. Calcium is Ca. Nitrate, ATE, is the clue, the signal to you that it is a polyatomic ion. It's NO3 off the back of your table. It has a -1. You look up calcium, it's +2. You need to crisscross. Okay, but you can't write a 2 until you put the NO3 in parentheses and added a 2. So your formula for calcium nitrate. Okay, it's very important. These parentheses indicate that you need 2 of the group. Okay, you can't change any of the subscripts that you see on the back of the periodic table. You can't change the subscripts on those polyatomic ions. Okay, if, however, you have a compound where you would not need to crisscross and put a number on the polyatomic ion, then you don't need the parentheses. Now this is sodium. Sodium is +1. Phosphate, if you look on the back of the periodic table, is -3. You need to crisscross, but the sodium is a 1. Okay, so you don't need to worry about anything. You just put a 3 here. So your formula here is Na3 PO4. No, I did not have to put the PO4 inside parentheses because when I crisscrossed it, a crisscross would be a 1, so it doesn't apply. Okay, time to pause or stop the video and go to your packet for the page entitled Polyatomic Ions and do a little practicing. Okay, our next compound are the acids. Acids are compounds that begin with hydrogen. In these, H behaves as a metal and forms a +1 ion. Okay, hydrogen is the one that is what makes things acidic. When we say that something's an acid, it can give you a chemical burn and all that type of thing. Okay, it's actually the H+ ion that does all of that. So these are made of two groups. There's the binary acids, and that's H+ plus a nonmetal ion. And then there's the polyatomic acids. These are comprised of H+ plus a polyatomic ion. Now, we're going to name and write formulas for these a little bit differently. Okay, so we're going to do binary acids first. Okay, we name them. We're going to start with a prefix. The prefix will be hydro. And then there's going to be something, ic acid. The something is going to be the root of the nonmetal that the hydrogen is paired with. So for example, HCl, okay, is hydrogen and chlorine. So this is going to be called hydro. The root of chlorine is chlor. Hydrochlor is the root. Ic acid. HF would be called hydrofluor, because this is fluorine, fluoric acid. Now if it was paired with nitrogen, so I would have a 3, because the nitrogen ion has a -3 and hydrogen's +1. This would be called hydro. And the root of nitrogen is niter, N-I-T-R, nitric acid. Okay, the formula writing is easy. H will be +1. Okay, and then you'll crisscross or cancel with the nonmetal ion. Okay, so for example, hydrosulfuric acid, that's H+. Sulfuric means that's its sulfur, which is -2. So I'm going to crisscross that. Okay, the 1, the 2 goes down here. So hydrosulfuric acid is H2S. Okay, for the polyatomic ions, the polyatomic acids, okay, we're going to name ic acid. No hydro. Okay, so polyatomic acids are normally named something-ic acid. Okay, so they look just like the binary acids. That's where it gets confusing, except they don't start with hydro. So hydro something-ic acid means it's hydrogen plus a nonmetal. Something-ic acid means it's hydrogen plus a polyatomic ion. Now, this is the tricky part. If the polyatomic ion ends in ITE, we're going to use a different ending, OUS. It just is a little bit confusing for these. So for example, HNO3, this is the polyatomic ion. This is nitrate. So we're going to name it. The root is niter. Ic acid. Okay, here's another acid, C2O4, called oxalate. So the root would be oxal, oxal, ic acid. Okay, this is sulfate. So this would be called sulfur ic acid. Sulfur and phosphorus you got to watch a little bit because their roots aren't exactly what you see right there. So sulfate, the root is not sulf, the root is sulfur, which is kind of weird. Now with let's for example H3PO3. This is phosphite. Okay, so we would call this phosphorus acid. Okay, these don't occur very often. There's really only three: sulfite, nitrite, and phosphite. Okay, so and chlorite and hypochlorite are there too, but there's not this. There's much more of the ATEs, and IDEs are treated the same way as ATEs. So formulas are really easy. It's H plus the polyatomic ion, and you just crisscross or cancel. Okay, so carbonic acid is H plus. Okay, this is carbon, so you go and you see what has a root of carbon. It's carbonate. Okay, you're going to just crisscross. So this means the 2 comes over here, the 1 we don't care about, H2CO3. Okay, so it's time to pause the video and go to the page that's marked acids and practice those. Okay, our last group are covalent compounds. This is a very, very different from everything we've been doing because these are all nonmetals only. There are no metals. No ions, no oxidation numbers. Okay, these are unique because they will use prefixes to show how many atoms are in the molecule. Okay, these are the prefixes you're going to need to know. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, and 7 is hepta. So for example, SF6. Now, the only tricky thing, we have to drop the mono. We have to drop off the first element. Okay, so mono would only be used if there's only one of the second element you see. Okay, so there's one sulfur. That would normally be mono, but since it's the first element, we're going to drop off the mono. We'll just call it sulfur. There are 6 fluorines. 6 is hexa, so we're going to call it hexafluoride. CO2, there's 1 carbon. That would normally be mono, but we drop that off the first element. There's 2 oxygens, so it's di. So we're going to call this carbon dioxide. The thing that's confusing is they still have endings like they were ions, but they're not ions. There are no ions in a covalent compound. So that is what is very, very, very confusing. But if you see these prefixes, and you notice that both the elements are to the right of the stair-step line, you know it's covalent compounds. Okay, so let's practice going a little bit the other way. Okay, if you were going to name this compound, there are 2 phosphoruses. 2 is di. So it's diphosphorus. Then there are 5 oxygens. 5 is penta. Okay, the second element is named as though it was an ion, so it's pentaoxide. You can also drop off the A. You do see that sometimes, especially with oxygen. It would be called diphosphorus pentoxide. Okay, what about this compound? C is obviously carbon. There's 1 carbon, but we're not going to use that, so it'll be carbon. This is oxygen. There's 1 of them, so we will use mono on the second one. Now the only tricky thing is you have to remember with monoxide, don't put 2 O's, otherwise it looks like monoxide. Okay, so when you're doing some naming, okay, just remember you look at the subscripts, and those become the prefixes. Okay, so it's time to stop the video and work on the last page in your packet, which is covalent compounds. Good luck. Have fun.